So in this care package right now, we're just going to quickly go through it. So I'll empty this onto the table. Hope I can hear some really cool toys in here. So, whoops. Okay. Oh, and Paul mentioned the space agency, and I think everyone may have got some space agency goodies in here. That includes this really awesome space agency pen. I don't know how many people have already played with this, but it's really cool. You can kind of undo the back of it, and you have a screwdriver here. So be careful with this because it's a little bit sharp. So make sure your parents know that you have this pen. And then here you have a ruler. I remember I used to have one of these in primary school. I did lots of physics measuring with my little ruler pen. And then if you twist this top, you'll have the pen itself. So this is a very cool pen. Either if you're, also there's a level in here. So it tells you how flat something is. So of course you have a little bubble in here. And as you move the pen up and down, you can see the bubble move and you can work out how flat things are. So this is a very cool pen. This is like a science kid's dream of a pen. But anyway, let's move on because we have to actually do the physics experiment. Also, wait, there's this really cool Australian Space Agency sticker as well. And I'm pretty sure everyone would have got these. The Australian Space Agency swag. Very, very cool stuff. Oh, wait, there's even more. There's also this little badge here, the Australian Space Agency badge. So you can put this on your school bag. You can put this on anything, really. This is awesome. I wish I had all this kind of stuff when I was learning how to do science as well. But okay, the important parts here are the instruction sheet, which is very, very beautifully formatted. Look at this. Measuring gravity, that's what we're doing today. That's what all of you guys are doing today, all of you guys and gals. Then we had the bob. So we call this a bob in physics, but really it's just a weight. So it's the weight of the pendulum. And then we have the pendulum string. And maybe you got a couple of these strings just so you have a couple of duplicates. But yes, then we have this string. So this string is for the pendulum. It's probably quite hard to see on the camera. Am I just kind of like holding up nothing in the air? Anyway, we have the string, we have the bob, and we have the instructions. This is what we need for our experiment. This is what you got in your experiment manuals, but there's a couple of other things that you'll need as well. So we have this meter-long ruler. You don't need such a long ruler, but you will need a ruler because as you'll find out today, we have to measure the length of this string for your pendulum. This is how we're going to calculate gravity. So we need a ruler for measuring gravity. So make sure you have a ruler. And you also need some kind of timer. So my timer is just going to be my phone. So I'm not too sure if parents are out there listening in. Make sure your young scientist has a timer and they also have a ruler. These things are very important. So now we're just going to have a general setup. The instructions here are in the kind of blue part. So the instructions how you set up your pendulum are in the blue part of the instructions. And there's many excellent hints and tips how to properly do good science, to plan and predict, to measure and record, to calculate and analyze, and all these things. So make sure you read this. Hopefully a lot of you have read it already, and maybe even some of you have already done experiments, which is a very good thing to do. In science, we like doing as many experiments as possible. But I think the easiest way to start this off is just kind of threading your thread through the pendulum like this. Your thread's gonna pop up on the other side. And I hear many of your scouts. So I want you to just tie a knot here. It doesn't have to be anything fancy. I'm just gonna do a double knot. I don't know what the technical word here is, but I'm just gonna do a double knot. It's you know, you just do kind of a crossover twice, just something to secure the bob, secure the weight. Okay. Well, I'm not very good at doing double knots, apparently. I'm a theoretical physicist. This is my first experiment I've done in a year. So here we go. Okay. So now this is properly fastened on to the thread. You can see I have some thread hanging over on the end here, but it doesn't really matter. This won't really affect my experiment too much, or at least I hope. Okay. So another thing that I should have mentioned is, yes, we got all this excellent bob and the string and the instructions and all the space swag, but we also got some blue tack, and our blue tack is going to let us fasten our pendulum to a table. So here's a table we've prepared earlier. So this is a table that you'll need some kind of table, something to fasten your pendulum to. What you want to do is just stick your, actually, let's do this the other way around. So get your pendulum. We're not too worried about how long it is right now because we're going to measure it, of course. And we're just going to fasten our pendulum to the table like this. And there we go. So make sure it's nice and fast. Give it a good squish on there. And if all things work out, your pendulum should be pretty much just hanging, not doing too much. Mine's rotating a little bit because it's a little bit wound up. It has a little bit of angular momentum, just unspinning itself slowly. But this is what it should look like. It's just hanging here. Okay. And, well, how do we measure gravity from this, right? How do you measure gravity from this? This is the question. Well, gravity is pushing down. It's pushing down on this pendulum. It's a thing that when I perturb the pendulum, so when I take the pendulum from its vertical position and I bring it up a little bit and I let it go, gravity is the thing that's accelerating it down. It's the thing that's making this pendulum swing. And in fact, there's a relationship between how long it takes the pendulum to swing and how long this piece of string is. And we are going to be using that relationship today to work out the strength of gravity. Everyone is going to do it. All over 200 of you are going to measure gravity, and we're going to be doing a little bit of statistics behind the scenes, and we're going to be showing you what the measurement of gravity is. So hopefully we get something close, but who knows? Okay, so as I said, two things we need to measure. We need to measure the time it takes to go from one side of the pendulum to the other side. This is called the period. And we have to measure the length of the pendulum. Okay, so let's do the first one. So I have my big ruler here. You can use any kind of ruler. And I'm going to measure from the middle of the pendulum bob. So from the middle of the bob, I hope you can see that, from the middle of the bob, which is around there, up to the anchor point. So that the very start of the anchor point, which is at the end of the blue tack. So do you want to scroll up here? So right to the anchor point, right there. Okay, so that's what I'm going to measure. And it looks like mine is 36 centimeters-ish. And I say ish, but I want you to measure it as accurately as possible. Okay, so 36 centimeters, it looks like it's 36.5 centimeters, or maybe a little bit more. 36.6 centimeters. I think it's 36.6 centimeters. Okay. So back in our instructions, we have this excellent table of measurements here. So here it's measurements, and I'm going to record my information. L, the length of my pendulum, is equal to 36.6 centimeters. So this is what I've written here in my measurement column. So as scientists, we have to record everything that's happening. And of course, the L is a very interesting part here. So we have to record our L. So you will be reporting this L into our Google form that we'll show you about soon. So the next thing we want you to record is the period. Remember, we had some kind of relationship between the length of the pendulum and the period, the time it takes to go from one side to the other. From that relation, we measure gravity. So I need to take my stopwatch. Here's my stopwatch. And I'm going to, in this first run, we're going to have just a very, quite a small kind of starting position. So this is the vertical, and I'm changing the angle, and I'm changing the angle only to be quite small. Nothing like this. Like this is like a 90-degree angle, right? So this is a 90-degree angle with respect to the vertical. So this is too large. If I do it up here, the pendulum's going to go crazy. It's all kind of wild. It's wobbling all over the place. So we don't want to do that. We want to have a very controlled starting position. So let's go to about here, okay? And I'm not going to let it go and push it like this. Of course, that's not going to work either. We're all doing this experiment, and we all have to do it exactly the same way. So this starting position is very important. We don't all have to have exactly the same starting position in terms of angle, but we can't release it with any extra velocity. We have to try to control this as much as possible, have as few moving parts as possible, okay? So I'm just going to release my starting angle. I'm going to have my stopwatch in my hand. I'm going to release it. And what I'm going to do is let it go for 10 times I'm going to record the value for 10 times, okay? So let's, are you ready? I'm going to release it and start my stopwatch. Go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Stop. So for me, that took 12.58 seconds. So in your measurement column, here you have time. Oh, I just noticed you have length here. So let me cross that out and put 36.6 centimeters. So this is my pendulum, 36.6 centimeters. Okay. My launch angle was small. So that was the angle it was away from the vertical. So small. And the first time was 12.58 seconds. So now I've got my length, I've got my first time, and I've also indicated that the angle that I had away from the vertical was quite small. So we're going to be repeating this experiment 3 times. So of course, we want the best kind of statistics, the best kind of like measurement of uncertainty here. So we want to repeat these experiments many, many times and kind of average over our data. So that's really what everyone is going to be doing. I want you now to kind of get set up, get organized, and do this experiment yourselves. We're going to open up the chat for a little while. You can ask us questions. We'll help troubleshoot the experiments. Yeah, so that's it. I'm really looking forward to it, to seeing your data. This is exciting. While Ryan is processing all of your excellent data, I'm going to talk to you a little bit about what we expect to see from Ryan in terms of how we're going to visualize or interpret all of this 200 odd experiments. And remember, that's 200 times 3 experiments. So what's that? How many experiments is that? Can someone tell me 200 times 3?
Is it 11 billion?
Not 11 billion, Manik. But it's a lot of experiments. I'm sure Tim is.
Yep, we've got some mathematicians here, James. Yep, they've got it. 600 measurements.
Awesome. So what I'm going to do is share my screen with you all. I'm going to do a little bit of work on my iPad right now. So my iPad is where I do a lot of my mathematics and my theory. Hopefully everyone can see my screen here. So of course, this is what we've been doing today. This is measuring gravity. And I just want to very, very briefly talk to you about some of the plots that you're about to see. One of those is going to be a histogram. So maybe you could all send, so who's seen a histogram before? Maybe you can send that information to Tim, the questions. Who's seen a histogram before, Tim?
Yeah, we have got some people who have seen histograms.
Awesome.
But also some who have not. So yeah,
okay.
there's something new to learn. It's a cool tool. So tell us about it, James.
Okay, so like I said, we've been taking lots and lots of data from you, lots and lots of data. And as a lot of people point out, we have like 600 experiments. So how are we going to somehow use all 600 of those experiments and show you information about how we've measured gravity? That's the question, right? So we're going to create this histogram. What is a histogram? Okay. Whoops, let me just come and delete this. And delete this. So with any kind of plot, of course, you have a set of axes. So let's just draw our axes in here. So we have a y-axis and we have a x-axis. So on the x-axis, I'm just going to put the value of gravity. So that's going on my x-axis of this plot. So what I mean by that is if I get a value of 9.0, I'll put that value here. If I put 9.1, 9.2, 9.3, 9.4, 9.5, and let's go 9.6, 9.7, 9.8. Okay. So I've got all these different values for the measured values of gravity that are coming from your experiments, and I put those down here, okay? So on this y-axis, I put the number of experiments. So down here is the values of the gravity that you measure in a particular experiment, and up here is the number of experiments that have that value of gravity, okay? So I hope everyone's following this. But essentially, if we get a bunch of measurements, okay, so say we have all these measurements coming in, 9.0, 9.1, 9.1, 9.0, 9.2, 9.3, 9.1. So we have all these measurements. Remember, we'll have 600 of these measurements. So what a histogram allows us to do is to visualize how many times we have each one of these values in our data, okay? So essentially on this axis, it'll be like 1, 2, 3, 4, 5, just a count, just the number of times we've had that value of gravity in our experiment. So for example, if you can see, I can just count 1, 2, so I've got two 9.0s. So I would put a bar that goes up to 1, up to 2. So this kind of bar tells me that I've got 2 experiments that have had 9.0 for their value of gravity. Oh, I see I've got 1, 2, 3 9.1s. So again, I would have to draw a bar, 1, 2, up to 3 for my value of gravity. So this is really what a histogram is. You can imagine if we kept measuring gravity, if instead I didn't have 1, 2, 3, 4, 5, 6, 7 experiments down here, and instead I had the full 600, you would have all kinds of values, and you would have, you know, something like this. Hopefully you would have not too many values over on this side, because we all know from the first part of our event today that the value of gravity is over here. So what would that mean for a good data set? It would mean that the most common value in our data set should be around 9.8. This bar should be very, very large. That's what we're hoping. So we're hoping that all these other bars for all these other values of gravity are really quite small. Not many people got such extreme events like over here at 9.0. We're hoping that isn't the case. We're hoping that everything is mostly over here, close to approximately 9.81 meters per second squared, which is the gravity that we, on average, experience on Earth. So this is what Ryan is doing right now. He's calculating the histogram for all of your values of gravity. And of course, we're going to have a spread of values, as I've shown here, a big spread of values. How are you doing for time, Manik?
We're doing really well.
Okay. And essentially what we're going to do is we're going to compute the average of all of these values, and hopefully the average falls around here. So that's like the mean value. Of course, you'll learn all about these kind of statistics that we use later on in your schooling. But essentially, yes, we're hoping that all the values fall close to the true value of gravity around here. Of course, they're not going to be exactly the same, but we hope that they're kind of close. So that is what a histogram is. It encapsulates how many number of experiments we have with these particular values of gravity. So this is what we're computing in the background right now. So maybe Ryan, how are you going? Are you ready to show?
Not yet, sorry.
Not yet? Okay, that's fine. That's fine.
Science takes time.
Yep.
Yeah, we're doing actually pretty good though. I'll give you that.
Yeah.
There's a small
So I
measurement
think
are looking good.
we're getting very close to a result, which is exciting. Some people have asked, though, about parts of the experiment and how they were working. There were some challenges in the experiments. This is always the case. We always need to think about what went wrong, what could be better. So I recall some people were asking what might happen if we used a different string or a different type of thread. Would it change our results? This is a really important thing to consider, is there anything about our experiment that might give us an incorrect measurement? Could it change the time that we record? So it certainly could, but we just have to minimize these, make things as best we can. So that means making sure that the pendulum could swing freely, and making sure that the pendulum can swing for as long as possible. So if you're using some sort of string which is rubbing against the table a lot, then that's going to stop the pendulum. It's going to slow the pendulum down, and maybe by the time it's done 10 swings, it has almost stopped. It's only a very small back and forth. So that's important to consider, is how fast does the pendulum slow down, because that might change our measurements, or our calculations, sorry. So
Absolutely.
we're sort of assuming that it does go back and forth. It's very nice and free, but some of these things could explain why our calculations might be slightly off.
Absolutely. And this is why we sent out all of these very controlled experiments with the same string, the same bobs, the same kind of blue tack. We're trying to keep everything the same. We try to be the best kind of scientists we can possibly be. Remember, we want to control everything essentially, except for the variables that we want to change. So everything stays the same except for maybe one variable that we want to change. So that's the idea of doing a good experiment.
All right, give me one more minute. I've got all the figures now, and I'll just put them in.
Oh, I'm excited. Is everyone else excited? Send your excitement to Tim.
Ryan is not cutting any corners today, which is great.
Yeah.
And I think I also just saw an email of someone's pendulum set up. So please, yes, send us emails. Put them up on Facebook if you feel like you want to share them there. That'd be excellent. This is so cool,
right.
Being able to measure gravity with you all.
Everyone's very excited, sending through in the chat. They're keen to hear the measurements and how we went. Oh, somebody has asked, could the this is Liam has asked, could the constant for gravity ever change? What if Earth went through a huge cloud of dark matter that we couldn't see? Now, I think, I think Liam's asking about whether the fundamental way that gravity works could ever change. And
Great question.
In general, we think of this as a constant across the universe, that the laws of physics work the same way across the universe, and that should be true. But of course, some things, as if like dark matter, sometimes the way we see those forces, the way we see the universe can change, even if the laws are actually working the same way. But do you guys have any thoughts on that question?
So that's a really good question. If the Earth's mass changed a lot, we would be in a lot of trouble. So it's very fortunate for us that the Earth has a gravitational pull, and the acceleration of that gravitational pull is the thing that we've just been calculating. So is everyone ready? Before we get into the actual results, I'll just flash up some scary looking equations. So someone asked before about what we're actually using to measure gravity. So this is the equation or the relationship that we're using, this strange looking thing. So these things that have just got colors are the important things. This blue T over here is the period of the pendulum. So this is what we measure with our experiment with your stopwatch. This green L is the length of the pendulum. So that's what you measured with your ruler. So if you change L, T will also change. But this golden G, this is, oops, that's an incorrect text is what that is. That is what we're trying to solve. That is the acceleration due to Earth's gravity. So how does this all work? We rearrange that equation from before, and we have G is equal to 2 pi divided by the period squared multiplied by the length of the pendulum. So how many measurements did we get? We got 200. And is everyone ready for the results?
Yes.
Let's open up the chat and see how everyone's feeling.
I'm ready.
Good. Let's start with the worst one then. So let's look at the large angle. So this is still not too bad, but we've done better is the good part. So here is 9.81. So this is what we would like to find. This is what we measured. This is the mean of all of the results that you all took. So you did a fantastic job, even with a large angle. This is what we got for diagonal releases. You can see it's a bit closer now to what we want to find.
Oh, we're moving over. We're moving closer and closer.
Yeah, let's see the real result. We want to get a small drum roll going. Good. All right, let's see. And here we go. We measured together gravity of 9.47 versus 9.81. And that's incredibly close. We're off by 0.4. And that's an awesome job that all of you have done today. And I'm blown away by how well you've all done. These measurements are really close to the right value. They're really concentrated around the right spot. So great job, everyone.
Wow. So that we got it to an accuracy of like 96% of the true value. So that's really amazing, everyone.
Yeah.
And remember, we just measured something fundamental about the universe using a pendulum. So using a piece of string and a weight on the end of it. It's amazing. You are geniuses. I agree. So someone in the chat, I see. Awesome. Everyone deserves to pat themselves on the back right now. Let's get a good pat on the back.
That's not physical.
Well done, everyone.
Well done. Awesome work.